TC hasn't been officially closed yet. It asks for an extension by 1 year, so for another 1 year it will be active, but most of the research has been done, so at the moment it's mostly for publications of the results.
All right, excellent. Thanks very much. Hello, good morning everybody. I'm Dr. Bahman Ghiassi, Associate Professor of Sustainable Infrastructure Materials from University of Birmingham. As Enrico correctly mentioned, I'm here on behalf of the chairs, Maria Antonietta and Corina, who were not able to be present today to present the outputs of this technical committee. Now, obviously this technical committee is focused on inorganic matrix composites, or IMCs, which are basically a combination of, we call it a marriage between innovative composite materials and traditional materials. Is basically we're talking about textile reinforcement grids that can be found in different forms or shapes embedded in an inorganic matrix. Now, just to make it a little bit complex for everybody, you can see a lot of different acronyms for these materials in the literature. You can see TRMs, you can see FRCMs, you can see TRCs, and you can also recently see CRMs. There is so I'm a little bit joking, but also these different acronyms have come because of different reasons, because basically to be able to identify different types of textiles and matrices that are being used in these systems. So when we're talking about IMCs, we're talking about a wide range of reinforcement possibilities. Those could be simply textiles made of rovings that are made of thousands of multifilaments of glass, basalt, or carbon, or even natural fibers. But also more recently we see them as grids of fiber reinforced polymers, but at smaller sections, and those are mostly referred to as CRMs. Now, the application of these materials have started in around, the material textile reinforced concrete in general started to come out around 1996, 2000. Has been mostly used for repair or strengthening of existing masonry or concrete structures, but also for prefabricated structural components such as facades, and more recently for development of material efficient, what I call load-bearing structural components. Now, our TC basically have been mostly focused on the application of these materials to the strengthening of existing masonry structures. Yeah, and this TC has also relation to several other previous technical committees in Rilem. The first one on this topic was TC 201, which was focused on textile reinforced concrete. The output of that TC was a comprehensive literature review of this material and its applications for load-bearing or strengthening, load-bearing structural components or strengthening of existing structures. Afterwards, there was TC-TDT, which was focused on design methods and test methods and design of textile reinforced concrete. It led to a number of recommendations and guidelines for testing of these composite materials. Afterwards, we had TC223 MSC, which was focused on application of fiber reinforced polymers to the strengthening of masonry structures, which I had the pleasure of being involved in when I was still counted as a young member of Rilem, my PhD in 2010 to 2013. Afterwards, TC250 CSM started, which was focused on assessment of the shear performance of textile reinforced mortar or IMCs with masonry substrate. And that TC led to also development of a number of guidelines for testing the interfacial shear behavior between IMC composite and masonry substrates, but also some guidelines for the design of these systems. Now, at the minute, we have two actually ongoing TCs on these composite materials. One is 290 IMC, which I'm presenting today, and is focused on durability of IMC composites when applied to masonry structures. I had the pleasure of being involved in this committee as one of the chapter leads, and as well one of the co-leaders of the experimental work group that we followed. The other TC is TC 292 MCC, which is also reaching its end, and that was focused on updating basically the TC 201, and the main output of it would be a more comprehensive literature review report on the application, understanding, modeling, and case studies of these type of materials. I had also the pleasure of being involved in that TC and acting as one of the chapter leaders. Now, as I just mentioned, TC 290 IMC was mainly aimed at identifying the gaps and also understanding the durability of IMC composites when applied to masonry substrates. How did we want to do that? We followed three key strategies. The first one was developing a state-of-the-art report on durability of these systems under different environmental conditions, including under moist environments, under high temperature, under alkaline environments, and under combined environmental conditions. The status of that activity is that the literature review report has been completed and is going to be published quite soon. Then we had another activity which was focused on experimental testing. We called it initially round-robin test, but it was not really round-robin test. Now I'll explain why it was not, but that included conducting several durability experimental tests on a range of commercially available products. The status of that is that the experimental tests have fully finished now, and we're at the stage of analyzing the data, but also preparing 5 publications that are going to be submitted to Materials and Structures. Hopefully the first drafts will be ready in April. And the last output, or last basically objective of this TC, was proposal of guidelines for basically specifically for alkaline exposure conditions. That's also being drafted at the minute. Why alkaline exposure conditions? Because a lot of textile reinforcements that are conventionally used for the strengthening of existing masonry structures are either made of glass or basalt, and they're both susceptible to alkaline environments. So it's quite important to understand, first of all, what's the performance of these systems under such environments, but also to propose reliable test methods to assess that susceptibility. The TC had a large membership, basically. On an average, annually, we had 75 members from different countries, mostly from Europe and Italy, because it's one of the most popular materials in the strengthening of existing masonry and historical structures in Italy, but also we had a lot of members from other European cities, but also from Asia, from Canada, from Brazil. The key beneficiaries of this TC, we think, are first of all manufacturers who are interested in understanding the durability of the products they're providing under harsh environmental conditions. There are practitioners who are interested to design these materials for projects, whether it's for seismic strengthening applications or for strengthening of existing deteriorated infrastructure. And as well, the results are of interest for public and private institutions who are involved in developing design relations and codes to be able to design these materials properly. A few slides I have about the experimental testing activity that was followed during this TC. We had the pleasure of involvement of 6 different companies who providing commercial products for a strengthening of existing masonry structures, and that included TRM or FRCM system and as well CRM systems. In total, we had 18 products available to us, and that included those that are made of glass, basalt, carbon or natural fibers, and then for the matrix we were working with cement or lime-based mortars. Just for those who not very familiar with the field of masonry, lime-based mortars are the most common basically matrices preferable for strengthening of existing masonry or historical structures because of their characteristics in terms of deformability, but also compatibility with existing masonry materials. Now, these 18 different products that we had, we wanted to assess basically their durability under moisture and alkaline environmental exposures. We had 26 different research laboratories involved in these experimental tests. And the reason that I said this was not a round-robin test is that basically the large number of products that we were dealing with implicated that we had to have certain number of partners working on certain products. So we have certain partners working on certain, so 3 or 4, let's say at least, laboratories working on each product to see also a little bit of repeatability, but also to cover the whole range of products that we wanted to assess. The initiation of the experimental test of this TC was a little bit overlapping with COVID. So the tests stopped a little bit. We aged a couple of years, but our materials didn't age. So they were in our labs waiting for researchers to come back. In general, we followed 2 different procedures for evaluating the durability of the materials we wanted to investigate against moisture alkaline environments. One testing program was developed for TRM or FRCM systems, and the other one was for CRM systems due to their differences in the nature and physical, mechanical and chemical characteristics. For FRCM systems, we had a relatively complex testing program. We tested material constituents that includes yarns or textile reinforcements, the mortars that was coming with each product, but also the whole composite system as a component, basically. We conducted tests that are conditioned, basically we call, or reference conditions, but also then we exposed the samples to alkaline environmental conditions or hot water immersions as per CNR Italian guidelines or EAD guidelines. As you can see, there are some text here on the number of, it doesn't work. You can see some black text, and then you can see some red text. The black text indicates the number of tests that had to be conducted by each partner, so they were compulsory tests, but we were also interested to understand a little bit more the deterioration mechanisms involved, and as such we also defined sort of voluntary tests for those who were interested to conduct further experimental tests, and those are the red ones presented here. For alkaline environmental exposures, we had 2 different conditions. We indeed had 3, but for TRMs or FRCMs, we had 2 different environmental conditions. One representing the pore solution alkalinity of cement-based, basically, matrices, and the other one representing the pore solution alkalinity of lime-based matrices. And samples were exposed to those environmental conditions at different temperatures of 23 and 40 degrees. We also exposed samples to hot water, which was mainly, again, at 20 and 40 degrees. For CRMs, the procedure was a little bit different because as per guidelines, that have been developed for FRP materials. In these systems, only the reinforcement are usually tested, so we didn't test coupons of composite material. And that included also exposure to alkaline environments in a different set of conditions, but also hot water immersion conditions. Just a quick review of 3 different alkaline environmental conditions that we considered. As I mentioned, the first environment was representative of lime mortar alkalinity, let's say. The second one, cement mortars alkalinity. And then the third one was the one that was proposed by ASTM D7705 for evaluating the durability of fiber reinforced polymers under alkaline environments, and that was only used for CRM systems. Now, just a quick overview of the experimental results we observed. As I mentioned, we just had all our experimental data gathered. We faced a little bit of difficulties in experimental testing with COVID, as I mentioned. Several labs were not able to conduct their tests on time, but now we all finished. We're gathering the data, we're analyzing a little bit data, but just a quick review of what we've obtained, let's say. We conducted around 2,000 tests on 4 different CRM tests, which are basically fiber reinforced polymer grids embedded in lime or cement-based mortars. The key observation was that there was we saw a significant reduction of the mechanical performance of fiber reinforced polymers under the alkaline environmental condition that is proposed by ASTM. We're still further analyzing the data, and this is going to be one of the key publications that are going to be prepared as the output of this TC. The other set of tests were, let's say, combined as tests that were focused on glass-based textile reinforcement embedded in lime-based matrices, and they were type of FRCM or TRM systems. And the preliminary results that we've seen shows that when we're exposing these systems to high temperature water immersion conditions or high temperature alkaline environments, we see around 20% of reduction in strength or mechanical performance of these systems after the certain periods that the codes allow. That 20% is aligned with also the durability factors that have come already in the CNR or EAD design guidelines. So this is good, basically. The other basically set of experiments that we've done were focused mainly on we had 2 different types of basalt systems embedded in lime, and then a carbon system embedded in a lime mortar, and then finally an AR alkali resistant glass embedded in a cement, and an e-glass embedded in cement. Now the reason I'm presenting these glasses in a different combination is that because they were not embedded in lime, so we tried to combine the lime results and glass ones that were the majority of the products we were investigating in one set. That was the previous slide, and these are the ones that can be compared to those, but not directly. So that's why they've been presented in a separate, basically, combination. Now, some interesting results we found out was that alkaline-resistant glasses, alkaline-resistant glass fibers showed very good durability under alkaline environments, whether it was low or high temperature. That was really good. We saw a little bit of around 10% reduction in the performance after the exposures that were considered. But basalt, as opposed to what is generally believed, showed a significant reduction of performance under high alkaline environments. Apologies for that the text is a little bit too small here, and I can't even see it myself. So, sorry. So this one is quite also, well, is interesting, what was expected. Basically, the blue curves show that the performance of alkaline resistant glass FRCMs is relatively constant under different environmental exposure conditions, but the red ones are the ones that are E-glass, so under high alkaline environments. That's what is expected, right? But then we wanted also to have a reference to understand how E-glass behaves under such conditions. Yeah, finally, we had a set of natural fiber-based systems. We also had involvement of several laboratories and companies in this experimental program. The key focus was on two different types of natural fibers, flax and jute, with different architectures. And we also conducted durability tests under water immersion, under high alkaline environments produced by lime-based mortars or by cement-based mortars. The key findings that we had, again, looking at preliminary results that we had, is that both types of natural fibers, as expected, showed deterioration and degradation under environmental conditions that were considered, but jute showed the highest deterioration. So the significant amount of deterioration we observed in jute led to the fact that we didn't continue the test on jute, and we did the rest of the tests on flax systems. Thank you very much.